At this point in our study of electrophilic addition reactions to alkenes, we've seen at least two examples of electrophiles that contain full or more commonly partial positive charge along with a lone pair on the electrophilic atom that rebounds back onto the alkene. This type of electron flow leads to an intermediate that contains a three-membered ring consisting of the electrophilic atom and the two atoms of the alkene, in which the electrophilic atom has a formal positive charge. If we could engage an anionic oxygen atom in this kind of reactivity by, for example, connecting that oxygen to a good leaving group, we could accomplish the formation of an epoxide, a three-membered ring containing an oxygen and two carbons, through this kind of reactivity. This is the idea of electrophilic epoxidation, which makes use of an electrophilic oxygen atom, one connected to a good leaving group, to effect the formation of a three-membered epoxide ring from an alkene. Let's explore this analogy in more detail by focusing in on halogenation. In an electrophilic halogenation reaction, the alkene pi electrons coordinate to one of the halogen atoms, and an electron pair rebounds back onto the alkene as the leaving group departs. This generates a three-membered halonium ion intermediate, which, because of its overall positive charge, is opened very rapidly by the halide anion to form a vicinal dihalide. The point I want to make here is that if we replace this electrophilic X atom with an oxygen, we generate a building block that's capable of the same type of reactivity. Because oxygen is in group 16, this fragment has a formal negative charge. And another key here is that in order for this reactivity to work, this oxygen needs to be connected to a good leaving group, for example, a halogen atom or some other type of good leaving group. This building block of the electrophilic atom with three electron pairs and a single bond to a good leaving group is analogous to this building block, an oxygen with three lone pairs connected to a good leaving group. Notice, though, that if we applied this same electron flow to this reactant, we would end up at a product with a neutral oxygen in a three-membered ring. And this is, of course, an epoxide. This suggests a strategy for electrophilic epoxidation of alkenes. The trick is finding the right reagent that supplies this molecule or a molecule like it that can engage in this kind of electron flow. The silver bullet here turns out to be a type of molecule called a peracid. We'll look at peracids in detail in a second, but for now let's just clarify this analogy by drawing curved arrows for the reaction of O-Lg with an alkene. In fact, the electron flow is exactly the same. The alkene attacks the oxygen atom, oxygen rebounds onto the alkene, and at the same time the leaving group departs with a pair of electrons. This results in the formation of a neutral epoxide and Lg-, the conjugate base of the leaving group. Provided Lg- is stable enough, it won't open the epoxide immediately, since the epoxide is neutral, where the halonium ion was positively charged in the case above. O-Lg here is really a theoretical reagent. If we tried something like O-Br or O-Cl, this kind of reactivity turns out not to work so well. A nice balance of good leaving group ability with an electrophilic oxygen atom that has the potential to be delivered to an alkene in high yield and selectivity is called a peracid. This molecule is called a peracid because it's a carboxylic acid with an extra oxygen atom. Notice that if this oxygen were not present, this would simply be a carboxylic acid. It's really this oxygen that's key to the reactivity of the peracid, the one jammed between the carboxylate oxygen here and the acidic hydrogen here. This oxygen is the analog to O- in this hypothetical molecule. Peracid epoxidation happens in a single step in a syn-type fashion through electron flow that's highly analogous with halogenation. The alkene donates a pair of electrons to the electrophilic oxygen atom. At the same time, a lone pair on this oxygen rebounds, forming a bond to the other carbon of the alkene. The entire carboxylate group here, which I'm highlighting in red, acts as a leaving group in this reaction. And this fragment corresponds to Lg in our hypothetical intermediate on the left here. Simple departure of the leaving group with a pair of electrons would leave the oxygen positively charged. But thanks to the magic of the peracid's geometry, the carboxylate can depart with a pair of electrons while deprotonating the electrophilic oxygen at the same time. These four curved arrows indicate that a lot is going on, but notice that this is just halogenation, the electron flow of halogenation, with a little extra proton transfer flare thrown in that avoids the formation of a positively charged oxygen. Since all of this electron flow happens at once in a single elementary step, the addition of oxygen is syn. This means that stereochemical relationships in the starting materials are preserved in the products. For example, if the starting alkene is trans, let's say we had another R group on the other carbon in a trans position, the product epoxide will also be trans. On the other hand, if the starting alkene is cis, say we had another R group in a cis position in the starting material, the product epoxide will also be cis. In this respect, this reaction is stereospecific. Starting with a cis alkene leads with 100% fidelity to a cis epoxide product, and starting with a trans alkene leads again with 100% fidelity to a trans alkene product. But as we've seen in other cases, when a chiral product is generated, let's say the two R groups were different so that the resulting product doesn't have a plane of symmetry, we should expect a racemic mixture of two enantiomers out of this reaction. One last point about electrophilic epoxidation is that this is a really nice reaction for introducing oxygen into a molecule, which can then be used for further transformations. For example, we can take this epoxide on and do SN2 substitution or other types of reactions and really start generating structural complexity from a relatively simple alkene starting material. Epoxidation with peracids converts an alkene into an epoxide, and the byproduct of this is a carboxylic acid, the peracid with its extra oxygen missing. The two practical reagents used for this purpose are peracetic acid, which looks just like acetic acid with that extra key oxygen jammed in there, and the rather exotic sounding metachloroperbenzoic acid, which you'll see abbreviated as MCPBA. The chlorine in this structure makes this molecule somewhat more electrophilic than peracetic acid, meaning it reacts a little bit more rapidly. For my purposes, you're welcome to use both, and you're welcome to use the abbreviation MCPBA. Because the reaction is concerted, cis groups in the alkene remain cis, and trans groups remain trans. This means that stereochemistry is retained, and the basis of this is the syn addition of the oxygen atom to one side of the plane formed by the alkene. Even though this addition is syn, oxygen can approach from above or below the plane of the alkene with 50% probability for each if the alkene is achiral, meaning that we should expect a racemic mixture in cases when a chiral product is generated from an achiral alkene. That would be the case for this trans epoxide, for instance, that lacks a plane of symmetry, and that would be the case for a cis epoxide product that lacks a plane of symmetry as well.